In order to solve this problem, let's first analyze the units. So charge density has the units of current per square meter. And remember that a current is a coulomb per second. So in other words, this is coulombs per seconds per cross-sectional area. And over on the right, we see that the T is going to have the units of seconds cubed. And the R is going to have the units of meters, and we have an R squared there. For all the units to work out, our mysterious little 5 there must have the units of seconds to the 4th on the bottom, with meters to the 4th on the bottom, with a coulombs on the top. And when we check the units out from there, we see that everything would cancel out to give us what we have on the left-hand side. For the next part of the problem, we now want to find the magnetic field inside this hypothetical wire with this non-uniform charge density. First thing we should do, like we do in most physics problems, is we should draw a picture. And I'm going to draw a cross-sectional view of the wire as well as a side view of our cylindrical wire. In the cross-sectional view, by looking at the function, we can see that the charge density is greatest at the center of the wire, and then, I should say current density, and then the current density is weaker and weaker as you get closer to the outside edge of the wire. And by drawing this picture, we can hopefully see that we have, again, a non-homogeneous distribution of current. And on the side view, there'd be a strong current inside the wire in the very middle, and then it would get weaker and weaker as we get closer and closer to the edges. And we'll label our vectors with an I, as we should label all vectors at all times. Okay, so because it is non-uniform, this means that we're going to integrate. And we first need to remember Ampere's law. Ampere's law is that the closed line integral of the magnetic field is going to equal mu naught times the current enclosed by our Amperian loop. And we always have to define our Amperian loop. Let's define it as being somewhere inside the wire, and it's going to have a radius of r. Now, the left-hand part of our integral is going to turn into a b times the circumference of our Amperian loop. That r is an arbitrary r that works for anywhere inside the wire, although not outside the wire. And then the issue we're going to have is we need to figure out how much current of the total current is inside that Amperian loop. And to do that, we're going to have to integrate over the area the current density, which is both a function of r and t, in Cartesian coordinates over in the x and in the y direction. Now, looking at the symmetry of this problem, it's going to be easier for us to use polar coordinates. Our charge density equation, our current density equation looked like this. And in polar coordinates, our dx dy turns into an r dr d theta. In the theta direction, we're going from 0 to 2 pi. And in the r direction, we're going from r from 0 to the radius of our Amperian loop. If we continue on a little bit more, I'm going to do this kind of backwards. I'm going to do the theta integral first. That's just going to turn into a 2 pi. And then in our r direction, I'm just going to be careful to multiply through by r before I integrate. The t is just going to hang out, as we're not doing anything with that yet. Our final solution will be a function of t. And then we're going to get 5/4 r to the 4th minus 0.003 over 2 r squared. The t cubed is still hanging out, and we're going from the center of the wire to the outer part of our Amperian loop. If we do a little bit of canceling and plugging or chugging and a little bit of rearranging, we see that the 2 pi's will cancel out, and one of the r's will cancel out over here. And that means we're going to get that the B field inside this hypothetical wire is going to equal mu naught times 5/4 r to the 3rd, subtract 0.003 divided by 2r times t cubed. And that would be the answer for this part of the question. Okay, for this last part of the question, we're asked how many coulombs of charge and how many electrons that might represent goes by a cross-section of the wire after 3 milliseconds. Well, first thing we need to do is we need to go back up above and remember that this part right here is the the current that is in our wire at a cross section. And thus the current is 2 pi times 5/4 r to the 4th, subtract 0.003 r squared, and there is a time dependence right there. We also remember that current is defined as the amount of charge that goes by per time period, so it's dq dt. If we're trying to find the charge, that's going to be the integral of I dt by doing a little bit of rearrangement. And that means we need to integrate the above function. And what I get when I integrate this in my head, which is, of course, always dangerous, is not much happens in the inner part of our brackets right here, but that, this should have been a t to the 3rd right there. But the t to the 3rd is going to go to a 1/4 t to the 4th. And we're integrating from 0 to 3 milliseconds. At this point, you can just plug and chug numbers in. I'll let you do that part at home. And of course, to find the number of electrons, we take our charge and divide it by the charge on a single electron, which is 10 to the minus 19 coulombs. The Q would be this right there. Okay, I hope that helps, and I'll see you tomorrow in class.